The moon was the first object for which we attempted to make good astrophotographs. The first photograph that we know was made by Louis Daguerre in Paris around 1839. He said he was able to capture a faint but clear image of the moon on one of his daguerreotypes. Unfortunately, the original was lost in a fire. We don't know what that looked like. From the next year, William Draper in New York did a series of lunar photographs for Manhattan College. And this is one of them right here. It shows a first quarter moon inside a little disc. This was the aperture stop of his telescope. This is the earliest surviving lunar photograph. And it started sort of a funny situation. Though throughout the 19th century, photography became more and more refined, and the lunar pictures became better and better. At no point in the 19th century did it even approach what you could do visually at the eyepiece of the telescope. This is a map made by Lorman, right about the same time that Draper was doing his lunar series, and you can see the difference in resolution here. I mean, you could sort of see some differences in coloration. You can see the disk, you can see the terminator here. Lorman was already mapping craterlets at that time. And through the 19th century, though the photographs were getting better, the best photographs published were actually of plaster models. Because there was no way for the photographs at the time to actually capture the details that you can see in the eyepiece. So Herschel very early on, Naismith and others would make plaster models of the moon, then photograph those, and those would then be reproduced in books. And they were honest about it. But it shows that photographing the moon isn't easy. And it's certainly hard to do it in anything like, these are both models of Copernicus, and Herschel being Herschel made a very precise model. Naismith being Naismith made a little bit more of a coarser model. It was more interesting what was going on around Copernicus than in the bowl of the crater itself. But this situation continued, even into the Apollo era. Though the lunar photographs were getting better and better. The photo on the left was from the Consolidated Lunar Atlas, done by Gerard Kuiper at the University of Arizona for NASA. He used a 61-inch telescope on Mount Bigelow, outside of Tucson, and produced some of the best lunar photographs of that day. And much of the preparation for Apollo was done with those Consolidated Lunar Atlas photos. But when the Air Force and U.S. Geological Survey cartographers went to actually make maps of the moon, they went back to the eyepiece of the telescope. They used the photographs to give them cartographic control to tell where the major features were. But when they wanted to film the details, they went right back to the eyepiece and did what lunar cartographers had been doing for centuries. And this situation continued into the 1990s, even with the coming of electronic technology and digital cameras, early CCD cameras and then consumer-grade digital cameras, lunar photography couldn't match what you could see with the eyepiece. We're in a different situation today. This is that photograph, considered one of the best photos of Copernicus taken during the age of film. This is a photograph I took from my backyard with modern video techniques, the techniques that Freddie was talking about. And you can see the difference in resolution there.
Ross, any way to cut, do you need that light?
Not at this second.
There's a lot of glare. That's good.
That shows a little bit better. Get better contrast there. You can see clearly there are some important differences here. You can see in the base of the crater itself, the fall back debris and the large ponds of impact melt. The details of the ejecta blanket outside of it, the details beyond that, and the secondary craters from Copernicus. Copernicus is about 93 kilometers across, so that'll give you a sense of the image scale here. With simple backyard equipment, we can now produce lunar photographs that were better than anything that could be produced during the age of film in large observatories. In fact, we're now at about the same resolution as the Lunar Orbiter 4 photographs, the first satellite mission that actually mapped the moon. Earlier lunar orbiters were very low altitude and could take photographs of small features. Lunar Orbiter 4 was the first actual mapping mission where they put the satellite up high enough that they could map large areas. Amateur photographs from the Earth are now at about the same level of resolution as the Orbiter 4 mapping images. Here's another image that I think tells the story very well. This is one of the best photographs of the crater Clavius taken during the age of film. It was taken from the largest successful telescope of the age of film, the 200-inch Palomar. This was considered to be the best image of Clavius taken up to that date. And it does show a lot of detail. This is the image from Midtown, taken last year. It has far greater resolution. We can note a number of craterlets here. Unfortunately, this PowerPoint projector isn't showing all the detail here. There's a little bit more detail visible. But there's much more information in a modern day video produced image. I mean, you can compare the floors of Rutherford here and see how much more detail you see in the hummocky fill. This is the crater Porter, named after the early 20th century amateur astronomer. The details that we can see in modern amateur-made photographs are far greater than observatory photos were during the age of film. This is an image that I took that I actually discovered in my archive a couple days ago. It's a picture on the left, whoops, I'm sorry. Picture of Copernicus I took, and as I was as I was going through the electronic version of the consolidated lunar atlas, I saw an old film photo that was taken under almost exactly the same lighting conditions. And even at this broad image scale, this is a fairly small scale image. We can see more detail and in the topographic features like the craterlets and the albedo features like the rays of Copernicus than you can see in the old photographs. And this was only on a moderate quality night, a night with relatively poor seeing. I was able to produce a photograph that greatly exceeded what they could do with film. Now, let me show you a little video. I'll come back to this in a second. The whole problem. Let's see, where am I? Let's see if this loads. Now, we may be straining the memory right now on the computer. Yeah, here it is. This is a video of Copernicus. In fact, it's the video I used for producing some of the images I'll show you today. The difficulty is mostly in the Earth's atmosphere. You can see how much that the seeing, the turbulence in the Earth's atmosphere, and most of this is at pretty high altitude up in the jet stream. Some of it is from my neighbor's house and her air conditioner, but you can see how the image is shimmering here. It's periodically being blurred by turbulence. There are image shifts, there are geometrical distortions. There's also a tracking error going on, causing the image to shift across the sensor. In producing a lunar photograph during the age of film, because of the focal lengths involved, and because the moon is a fairly faint object, it has the albedo of a lump of charcoal. It only reflects about 10% of the light that hits it. They had to use long exposures, and generally exposures were from about half a second to 2 seconds long. And so all this shimmering, all this blurring would be integrated over perhaps more than a second and produce a very blurry image, even in a large telescope with a high theoretical resolving power. The limitation wasn't the size of the telescope, it was the blurring caused by the atmosphere. And the larger the diameter of the telescope, the more air it was sampling and the worse the blurring. So this is what we're up against when we try to make lunar photos. Let me get out of that. This is my lunar photography rig. The main telescope is an 11-inch Celestron SCT. I keep my telescope permanently mounted on a cart so I can wheel it around my yard. It's important to be able to move the telescope around if you're doing high-resolution imaging because the heat rising off the roofs of houses and off the air conditioning systems and heating systems will greatly disturb the image. So in order to be able to move around my yard as the moon shifts to get the best view, I have the whole telescope mounted on a cart. The scope itself is on an alt-azimuth mounting rather than an equatorial mounting. It's computer driven and will track the moon very well. All I have to do is point the telescope at the moon and on the little hand pad tell it it's looking at the moon, and it will then track it well enough from then on. It's much easier to use an alt-azimuth mounting than an equatorial mounting, which takes some time to align. If you have to be mobile, move that telescope around. In the case of lunar imaging, the slight amount of field rotation you get over the 3 or 4 minutes you're making one of these videos can be compensated for in the software that we use for stacking the images, so that it doesn't really matter. If you're deep sky imaging, you're in a different situation. Using an alt-azimuth mounting isn't an option. You really need an equatorial mounting. In lunar imaging, though, there's another interesting feature. You don't want to track too accurately. You want to move the image over the sensor a little bit. And this will remove the effects of dead pixels or hot pixels on your sensor. If there's some dust on your sensor, you'd like to blur that out. By letting the image dance a little bit over your sensor, you're not burning a pixel into the same place in the image. Since this is in Memphis in the summertime at least, I have to stay under mosquito netting. So I have an observing card with an accessory, a rolling accessory case. My laptop computer's on that. I have an observing chair right there, since I'll be sitting for a number of moments. And 4 minutes, the length of one of my captures, is enough time for mosquitoes to find me, so the mosquito netting helps a lot. I like to image the moon at different scales because each scale of photography shows a different kind of feature on the moon. The moon is different from, say, photographing a deep sky object or a planet, in which the larger the telescope, the better. Small telescopes will have relatively fuzzy details. Big telescopes will have sharper details. This isn't necessarily true on the moon. That you want that a small telescope that can photograph the entire disk at once can give you information that's very hard to get in a telescope with a longer focal length, where you have to piece together a number of frames to get that big picture. The moon shows structure at every scale you look at it. And because of that, it can be imaged well in small telescopes and large telescopes. So I have 3 different optical tubes on my rig. I've got the main Celestron 11 SCT tube, a 3-inch f6 refractor for taking a whole disk image, and then a 4-inch f8 sort of medium focal length refractor. Both of these are apochromatic telescopes, so I don't have to worry about chromatic aberration. For taking medium scale views. This is a camera I use most now. It's an ASI 120. It'll spit out, in the USB 2 version, it'll spit out 30 frames a second. There's now a USB 3 version I've been playing with that'll spit out 60 full frames a second. So it's quite a fast camera. Through a USB cable, it feeds into a laptop computer, which acts both for controlling your exposure and for collecting the image. And then I control the telescope through a second hand pad. This is the accessory cart. It's got drawers for eyepieces and filters and cameras. It's got a handle on it, and then it has its own little mask, its own little light, which I got from a barbecue, which works quite well. And then a mask for holding up the mosquito netting. These are the cameras I've used in the past. Originally, in the late 90s, you had to, our video cameras were usually webcams. And so this is a Philips webcam right here. You had to MacGyver an adapter that you could fit onto your telescope. Since then, there are a number of companies that make small video cameras, especially for planetary imaging. This is an Orion. This is the DMK-41 that Freddie talked about. And this is the ASI 120 that I'm using most today. Now in using this video technique, the first stage is to capture a large number of frames. We capture this as a video movie. This is Fire Capture, the program I use for doing this. It gives you a live screen of the image in the camera at the time. You have camera controls up here. The main control we use is an exposure control that determines how long the chip accumulates photons before it reads them out. We have some other controls as well. There's an amplifier control, a gain control, and a gamma control that controls the contrast within the image that you use for solving problems. In video imaging, this is the most important thing you need to look at. Once you focus the image, you've got to look at the brightness histogram. These are 8-bit cameras, so they distinguish 256 levels of gray. In this case, the darkest pixels are down here, the brightest pixels, pure white, would be up here. When taking a video image that you're going to process, it's very important not to span the entire range. You want to give yourself some headroom at the top, because as I'll talk about in a second, we use sharpening and de-blurring techniques that tend to brighten the brightest pixels. So you need to give yourself some headroom at the top of the histogram. So we first focus the image on the screen, we frame it up the way we want to, set our exposure so that we've got an appropriate span of brightnesses in our brightness histogram, and then we hit the switch and it starts collecting images. And with these cameras, I can collect a 4,000 frame video in a matter of a couple minutes. Most of my videos are about 4,000 to 6,000 frames. Any more than that, that's going to take upwards of 4 to 6 gigabytes of memory. Any more than that, the processing becomes really clumsy, and sometimes there are file size limitations, and you can't go beyond that. Plus, the mosquitoes will often get inside the mosquito net by that time. This is what a single frame looks like. It's not very impressive. This is one of the better frames from the video I took of Copernicus. You can see that it's a bit fuzzy. If we enlarge this a bit, we can see that it's got considerable noise in it. That noise is coming both from the random variation and the number of photons that are arriving from different points on the image, but also from thermal noise within the camera and noise that comes into the cable between the camera and the computer. A single image isn't much. This isn't very impressive. To turn this into a useful image, we take our video and we drop it into a program that, first of all, selects the best frames. It ranks all the frames in your video from the clearest to the fuzziest. It then aligns a fraction of those frames, and you specify that. Usually in say a 4,000 or 6,000 frame video, I'll stack between 400 and 1,000 frames. It takes those frames, divides them up into a number of, I haven't learned the buttons yet, a number of different regions, and then aligns for each frame in the video these little sub-regions, these little sub-frames, to a master image that's usually the best frame in the stack. And so it takes the pixels in a particular frame, say within that box, lines them up, gets a best fit relationship between that box and the master image, and then reads off each pixel as a level of brightness for that master image. What you end up with, and for each frame, they'll go through a number of these alignment boxes. Usually from 20 to a couple hundred of these alignment boxes. And over the course of collecting 400 frames, it'll make, for every single pixel in the image you're building, it'll make 400 measurements of brightness. So the goal here is to build a composite image that we can then process. That composite image has a huge amount of information in it. This is a comparison of a single frame here to the composite image based on this. And while this composite image initially doesn't look much better than that single frame, this is a stack. This image here is built with a stack of 400 different frames. It actually has much more information in it. We've gone from 8 bits that can distinguish between 256 levels of gray to a 16-bit image that can distinguish over 65,000 levels of gray, which is more than you can display on a computer monitor. But we need that discrimination when we start processing the image and stretching out the contrast in areas. It's corrected, that stacking process corrects that geometrical distortion that comes in because of turbulence, because of seeing. Each little craterlet is where it belongs. The shapes of the craters and other features is now correct. It's almost cartographically correct. This composite image is slightly sharper than usually the best frame in the stack. But the most important thing, as Freddie mentioned, is it's extremely low noise. With 400 frames, we have only 1/20th the noise that you would have in a single frame. And reducing the noise is critical because a number of the processing steps we're going to go through amplify that noise. So you need to start with an image with very, very little noise in it. Once we have that base image, we want to recover some of its original sharpness. And unfortunately, because of this projector, you can't quite see what we've done here. We have specialty blurring techniques that start with an estimate of the amount of blur caused by the atmosphere, and then attempts to compensate for that. This is that stacked image right here before the deep blurring. This is what it looks like afterwards. I think I have a blow-up of that. Yeah, this is a good example. I like to use Lucy Richardson deconvolution. It's an alternative to the wavelets processing that Freddie was talking about. In Lucy Richardson deconvolution, you estimate the width of the blurring that's taking place in that image. And this is blurring that's coming from a number of different factors. It can be coming from atmospheric turbulence, tube currents within your telescope. It can even be focus errors. It doesn't matter where they come from. The algorithm then takes the size of that blur spot and then attempts to subtract its effects from this blurred image. And the result is an image that reconstructs, that recovers much of the original detail before that it was distorted by the Earth's atmosphere, by defocusing in your telescope and tube currents and so forth. And what you'll notice in this, if you can see, I don't have my glasses, but I think you can see it here, is that there are a number of details in the de-blurred scene that actually you cannot detect in the original video, or rather in the original stacked image. De-blurring will recover details that you have almost no inkling of in the image that you're processing. If you look out here at some of the smaller secondary craters that were, this is material that was ejected out of Copernicus as bombs that formed their own craters around the ejector blanket here. If you look closely out here, there are a number of little dots there. These are real features that you can't even see in the original base image that you're processing. So deconvolution techniques can bring out a tremendous amount of detail that you didn't know. This is why we stack. The old philosophy was that you stack your best few images to get a nice sharp picture. The new philosophy, you stack a lot of images to reduce the noise, so we can then apply powerful algorithms like deconvolution to get a sharper image. We get a much sharper image this way than trying to start with just our best frames. We then do other processing that tends to exaggerate, tends to amplify the noise in the image. High dynamic range is a way of manipulating the contrast here. It's applied fairly subtly here. This is the original sharpened image up here. You can see this area by the terminator, but you can't see a lot of detail. In fact, over here it gets completely dark. Over here, on the other hand, it's so bright that it's washed out a lot of the contrast. What high dynamic range does is it imitates something that your eye does. It makes local adjustments in contrast. It reduces the contrast across an image and boosts the contrast within regions. So the darker areas become more contrasty. At the same time, the brighter areas become more contrasty. I'll show you, give you a little demonstration of it. This is the image without any high dynamic range toning. You do this in Photoshop or with special purpose software. If you simply take a photograph of a scene and then process it without working on without manipulating the contrast, the images always look quite flat and dead. They're much less lively than what you see in the eyepiece. By adding a little bit of high dynamic range toning, you reduce the overall contrast across the image, and you boost local contrast within the bright zones, within the midtones, within the shadows. And it brings out much more information. This image is much closer to what you would see in the eyepiece than the ordinary photograph image. And when you're doing regular landscape photography, you'll notice this as well. If you shoot a scene, say looking at a tree line in the forest, the sky above the tree line will have clouds in it. The dappled shadows below the forest will have details in it. If you take a photograph of that, you're either going to burn in all the clouds and the sky will just be white, or you leave that shadow underneath the forest dark and you won't see any detail at all. The application of high dynamic range techniques can bring out those details in the clouds and in those shadows by reducing the overall contrast in the image and boosting the local contrast. Now sometimes we take this to an extreme, like over here. The goal here was to bring out the details over here in the crater rays coming out of Copernicus. And this is done by greatly amplifying local contrast and reducing the contrast almost completely across the image. In fact, it looks rather flat as you go across here, whereas originally this was quite bright, this is quite dark by the Terminator. And then of course it drops off completely with the Terminator. So you can create both naturalistic effects that are a closer approximation to what you would see if you're looking through the telescope, and some rather dramatic effects that you would never see a scene like this on the moon. But it might be interesting to image this way if you wanted to emphasize certain features. Then we apply another technique that also tends to amplify noise before we do anything else. This is a technique called sharpening. We don't have the resolution here, but maybe you can see it. Yeah, you can see it better here. This is that image that had gone through the deconvolution, so most of the blur is taken out. We've applied the high dynamic range techniques. We see nice definition here and the lumpy ejecta blanket around the crater. Then we use a sharpening technique which makes the details more apparent. What this technique does is look at contrast down at the pixel level. High dynamic range toning looks at contrast across the image. Sharpening techniques look at contrast at the micro level. It takes pixels that, I don't know if I can demonstrate with my hands, if two adjacent pixels have a slight difference in brightness, it makes the darker pixel much darker and the brighter pixel much brighter, and that emphasizes the edges. Unlike in the deep blurring technique that can reveal details in the image that you can't see in the base image you're processing, these sharpening techniques don't bring out any new details, they just make the details you see much more visible. And so you get better, you can see, if you look at the fallback or rollback debris here in the basin of the crater, you get much more definition because you've got much higher contrast here. Many of these smaller secondary craters out here come in much sharper, and the details in this hummocky ejecta blanket are much clearer after we apply the sharpening technique. Now once we do that, we add some cosmetic adjustments. This is our processed image. Here, we've gone through that stacking procedure. We've adjusted the contrast using HDR techniques. We've done some other things. I've denoised it here. Sometimes when you do those first three things, you deconvolute it, and then you do the HDR processing and the sharpening. You'll bring up the noise level to the point that you can see it in the image. There are in Photoshop, some smart denoising routines that will remove the worst of that noise without making the image look artificially smooth. That stacking process always leaves you with a ragged edge going all the way around because your different frames, since the image has been dancing a little bit over the sensor. The original frame has a very ragged edge around it. You clean up that edge, adjust the overall contrast, and you've got an image that you can work with. This image shows some interesting things about Copernicus. Copernicus is a very young crater. It's less than 1 billion years old, which is young for the moon. There are surfaces on the moon that go back to its formation 4.5 billion years ago. But because Copernicus is relatively young, its features are quite sharp. You can see this heavy ejecta blanket right around the crater. This was slow-moving debris that poured out of the crater very late in the cratering stage. Around that are secondary craters, bomb-like chunks of debris that came out of the crater much faster, somewhat earlier, and then these light rays that look almost like drifts of snow off in the distance. Originally, for Copernicus, it's 93 kilometers across. It's got rays that go out almost 1,000 kilometers. So originally, astronomers thought that those rays were drifts of dust that fell almost like snow. Today we know that the rays were formed by highly pulverized debris that left that crater at extremely high velocity, about 3,000 kilometers per hour. And this is, rather than a drift of snow, this is more like a hail of bullets coming down across the landscape. And when these particles hit the surface, it dug up the subsoil, which is lighter colored than the darker soil around it. And this would not have been a pleasant, this area, even though out here we're a good several hundred kilometers from the impact of Copernicus, this would not be a nice place to be. Processing is an essential part of image building in lunar photography. This is a contrast to that. This is that photo of Clavius I showed you before. This is the unprocessed stacked base image. The contrast is washed out. It doesn't look like there's a lot of detail here. When people first get into lunar and planetary imaging using this video technique, they're often disappointed at the images that are produced. Once you process that image, though, a tremendous amount of information comes out. And this shows you just what a little bit of work on an image will do. Without processing, video imaging is nothing special. With processing, it beats anything we've tried in the past. This is a full disk image that I took with the smallest telescope I regularly image with. This is with the 3-inch refractor. The chip that the sensor chip in the camera is only 1/3 of an inch across. So you have to have a very, very small image to fit all of it on the sensor. And that 3-inch telescope will just fit the image of the lunar disk onto that sensor without spilling off the edges. But even at that scale, it shows some very interesting features. And in fact, it shows the most important features of the moon. This area here, this triangular area, is the oldest part of the preserved surface on the near side. This has been saturated with craters. It consists of highland crust, which has been pulverized by craters of a wide range of sizes. This surface is about 4.5 billion years old. It's between about 4.5 and 4 billion years old. This was followed in lunar history by a brief period of intense, very heavy bombardment. Much larger pieces. This is early in the formation of the solar system. The small debris had already been swept up. There are some large pieces flying around the solar system, though, and between about 3.8 and 4 billion years ago, there are a number of very large impacts, and they created these huge basin structures. We've got Imbrium right here, Serenitatis, Tranquillitatis. Here we have the Nectaris basin, this basin right at 3.9 billion. The Humorum basin right there. There are a couple other fragmentary basins in the south. These large basins dug very deep holes. Initially, they dug all the way through the lithosphere, the hard brittle material on the surface of the moon, down into the more plastic, hotter layers below. Since that material was plastic, it then allowed these craters to fill in. The bottom rose up again. But it left scars. Many of these basins have rings around them. And these rings formed as the surface of the moon relaxed, as material was flowing back into these very large, very deep craters. Over the next billion years or so, these big basin impacts fill with lava. The lava plains are quite dark compared to the light highland crust down here. These are mostly dark minerals like olivine and pyroxene. The highland crust is mostly very light-colored minerals like feldspar. And this is the brightness contrast on the moon is primarily a mineralogical contrast and reveals something about time. The bright, rough surfaces are very, very old. The darker, smoother surfaces that are less cratered are much younger on the moon. And then most recently, within the last billion years or so, there have been a number of large impacts. This is Copernicus here, Kepler, Aristarchus. These all impacted into great large lava plains. They spilled out large, long streamers of ejecta forming these rays. Tycho down here in the southern highlands with rays that stretch about halfway across the moon. This ray material is very fresh and looks quite bright. Over time, that ray material will darken because of charged solar particles changing it chemically. And so we've got a couple indicators of age here. Rough surfaces generally mean old. Smoother surfaces with fewer craters means young. Within a region, lighter material like these rays coming off of Tycho means young. Darker material around it means old. Similarly over here, lighter material like these crater rays is relatively young. The darker adjacent material is an older surface. So we can use the mineralogy and the brightness of the surface to give us a sense of the age of structures. What I'd like to do now is focus in on this area here. This is a very wide-angle view taken with a relatively short focus refractor. This is that same area. We've printed on the side here. This is south. This is north. This is that same basin, Nectaris Basin, which is the best preserved of the early basins on the moon. This is taken with a medium focus refractor, and you can see that the image scale is larger. Here's that recent crater Tycho up here with its rays stretching across, even crossing part of the Nectaris Basin right here. This is Mare Tranquillitatis. Get a little bit closer. Apollo 11 landed right here. And then this is the ancient edge of the ancient Serenitatis Basin right there. I'll zoom a little bit in. This is an image of the same region, the Nectaris Basin again, but this time taken with the 11-inch SCT that's working at f10. And we're now zooming, going from instrument to instrument, we're zooming in closer and closer. We have a much more restricted, much narrower field of view, but with each stage, more details coming up. These ancient basins, as they relaxed and return to a plane with the rest of the surface of the moon, a number of rings pop up. Geologists have located, this is a map of the rings that geologists have noticed in Nectaris. There's an inner ring here. There is a ring just beyond it, marked here. These rings generally have a very steep fault. It creates a scarp, and then behind that fault, the rock slopes away. There's a trough here with another faint ring. See parts of it right there. This is the Altai Scar, which is a very deep ring, and then geologists claim that they can see it continues over here, that has survived over here. Geologists claim, and I've never been able to find any evidence of it, that there's a fifth ring that's running right through here. There's just a little bit of whenever you see a mountain range on the moon, you're looking at a basin ring. That's evidence of one of these ancient impacts. And they claim that, I think the altimetry data is showing that there's another ring beyond this. These multi-ring basins have been found also on Mercury. They've been found on Mars. There's evidence of them on some of Jupiter's moons. So this appears to be this multi-ring feature for very large basins that appears on a number of different planets, but was first discovered in lunar photographs. I want to zoom in a little bit. Here, I want to look at this is the crater Theopolis. Theopolis is about 100 kilometers across. It's a relatively young crater. It's older than Copernicus. You can't see its rays anymore. Its rays have faded out. So we believe it's between about 1 and 2 billion years old. But it still has a sharp central peak. The rim is quite sharp, and you can still see distinctive terraces, part of the collapse process along the edge. Next to it is a crater of about the same size, Cyrillus, that's much older. It's about twice the age. Cyrillus is about 4 billion years old and was already well eroded at the time that Theopolis formed. And you can see how Theophilus's debris has actually filled part of Cyrillus's floor right there. So originally they started as very similar craters, but over time as craters age, the walls become rounded off. The floor begins to fill with debris, and in the event of when Theopolis formed, it almost destroyed Cyrillus itself. This is taken with that same 11-inch Schmidt-Cassegrain, but with a Paramate, essentially a Barlow lens that doubles the focal length, allowing us to get a higher power image of a much narrower field. We'll shift over a little bit. Now we're going to look at this area here. This is the Altai Scar, one of the intermediate rings in the Nectaris Basin. This is a 300 kilometer length of scarp along here. This is the crater Piccolomini, which is it's about 50 kilometers across. That scarp itself is quite dramatic. Most of the features on the moon are rounded off. In raking light, they look like sharp pinnacles, but usually mountains on the moon, central peaks on craters, are pretty rounded off. They're pretty blunt. The Altai Scarp is one of the few features of the moon that really isn't. That scarp is 3 to 4 kilometers tall. If you saw this, it would look like a wall looming in front of you. Once again, this is one of the basin features that occurred when the lunar surface around Nectaris relaxed after the crater was formed. This is another example of a basin. Much of lunar geology and lunar photography is looking at the effects of basins on the landscape, and they have a wide range of effects. These basin impacts had an effect on the area for 1,000 kilometers around the basin itself. This photograph was a particular challenge. The whole Humboldtianum basin is located right on the lunar limb. Sometimes the face of the moon actually nods back and forth and up and down a little bit. So we can see total about 60% of the moon. This is in the position equivalent to where the moon's ears would be. I timed this photograph so that it was in a particular, the moon had tilted just enough to put the basin right on the limb of the moon, right on the edge. And this shows a couple things. It shows that we can see an inner ring of mountains here, an outer ring. That outer ring is about 500 kilometers across. But you can also see that though originally this was a deep basin, this basin probably originally was about this shape. It's relaxed probably within a few years of its original formation as the hot rock underneath it flowed up underneath. It's relaxed to now cover the curve of the moon. If you're standing right in the center of the basin, you wouldn't be able to see the rim here. You would be able to see the edge of these rings. The original crater was probably about that wide, originally about 500 kilometers across. This is the crater Atlas right here, or that's Atlas and Hercules, and I always forget which one's which. But you can see these little dark spots, which represent volcanic vents that had more recently had material well up and create a plume of volcanic ash that shows very dark in that photograph. This other crater here, which is either Hercules or Atlas, and I don't remember which, has a floor which has actually risen up and cracked because of magma that's welled up through the fissures that form from the cracks in that basin in that crater forming process. The largest basin forming impact happened about 3.85 billion years ago on the moon. forming the Imbrium Basin right here, which is now filled by the Sea of Rains. This basin is about 1,000 kilometers across, and the blast from the basin scoured the moon for the distance of another about 1,500 miles beyond that. This whole area here was scoured out by a blast of debris that created instant topography. And that's what this photograph here is showing. It's an enlargement of this area right here. See these lineations? The Imbrium Basin is, you can see it, is about up here, right? It's about 1,000. This image is a bit more than 1,000 kilometers across. The Imbrium Basin would be up here. The blast was so powerful that it scoured out these lineations here. All the edge of the basins and craters have been ground away by debris. It shows it very nicely. This is the crater Euclid right here. It shows it very nicely around that. This is called Imbrium sculpture. In the first few minutes after the impact, the blast of debris created valleys that were several kilometers deep and ridges that were a couple kilometers above that. It instantly transformed the topography around it, and much of the near side of the moon is dominated by topography that had been scoured out as part of this impact almost 4 billion years ago. Other features were also related to that impact as well. These are the Hyginus rills right here. This is a large linear crack that formed when the material flowed back into the Imbrium Basin. It created tension on the surface of the moon. Those cracks are so deep that they stretched down to the lunar mantle, and magma came up. And there's a series of volcanic pits that run along that rill, run along that crack, and a large volcanic caldera in the center. The volcanic features of the moon mostly came about because of impact processes, because of the fractures created by these large basin-forming impacts and local craters. Now, on the moon, there are a number of different volcanic styles. This was published online by Chuck Wood, who is he made his career as a lunar volcanologist. He's a lunar geologist and runs the Lunar Photo of the Day blog. I knew that he was interested in lunar volcanism while I was taking a whole moon image one day. I noticed that 3 volcanic terrains were right on the terminator and were showing up very nicely. So I made that image knowing he would bite when I sent it to him, and he published it the next day. This shows 3 very different styles. As I mentioned, we only see 3 different styles of volcanism. As I mentioned, we only see volcanoes in association with impact structures on the moon. The Marius Hills is an area of volcanic cinder cones. These are the few cones that we actually see on the moon. Most lunar volcanoes aren't like terrestrial volcanoes, but these are. These form in layers of eruptions over a long period of time. There are well over 100 documented domes, or documented cinder cones in the Marius Hills that built up from eruption after eruption, primarily of volcanic ash. This is a different kind of volcanic structure at the Mons Rumker. This originally was classified as a mountain, but as you look closely, it's actually a pile of lunar domes. Lunar domes are like shield volcanoes, like you see in Hawaii, and there's some shield volcanoes in Iceland as well. These are made of relatively runny lava that piles up, instead of in a steep cone, in a large shield-shaped structure. These are very common on Mars as well. In the case of the moon, sometimes we see individual shield volcanoes, individual lunar domes, but in this particular case it's peculiar because we have a number of domes that have come up on top of one another. And each of these domes has a little summit pit that represents the volcanic vent. The Aristarchus Plateau right here is a 3rd kind of volcanic structure, and it's unique on the moon. It's part of old terrain. You can see, if you look closely, you can see the lineations here. These are the Agricola Mountains. You can see a linear valley between them, and then here you can see little short linear segments. Some striations there as well. This is another example of Imbrium sculpture. This comes from the other side of the Imbrium Basin, over here. That first photo in Imbrium sculpture was that area. We're now on the other side of the basin. These were scoured out off of the ancient landscape, a landscape that goes back about 4 billion years. It was then scoured by the Imbrium impact, and then more recently, lava or magma pulled up underneath it, pushed it higher than the area around it, forming a plateau, and then broke through the surface. This is a large vent called the Cobra's Head, which represents a source of magma that then ran in a river, cutting its own valley. This is called Schroeder's Valley. There are a number of other examples of these sinuous rills running off. There's some up here too, and some over here as well, running off of the Aristarchus Plateau, which then filled up the entire Oceanus Procellarum, the ocean of storms, with lava. This is the vent that created this large dark area on the moon. This lava traveled over 1,000 kilometers. Lunar lava is usually very runny. It's about the viscosity of hot maple syrup. And so a lava flow can travel quite rapidly a distance over hundreds of kilometers. And these are the source vents for the Procellarum lavas, which are one of the largest features on the near side of the moon. Later on, an asteroid knocked, long after this whole area around here filled with lava, an asteroid knocked this crater, Aristarchus. Aristarchus, I believe, is about 40 kilometers across, and punched through the very light-colored substrate here. It's one of the brightest places on the moon, and very difficult to photograph with a color camera, because you always get color fringes. It's so bright white, it's almost like a star. You'll get color fringes around it that are very frustrating to try to photograph. This is one of the few lunar mysteries that survived the Apollo era. With Apollo, we learned an awful lot about the moon, and we're able to make a lot of sense of it. This is called a lunar swirl. It's one of 15 or 16 structures on the moon that still puzzle lunar scientists. Seen in ordinary white light, it looks mostly like this. Over in this, I apologize, this is now a little bit out of focus, but over here you can see that little brightening. That is this swirl. It's easy to spot in a telescope. It looks a little bit like a light-colored crater ray, but it doesn't point back to any crater. When you heavily process the image, it becomes a little bit spooky. It looks a little bit like a tangled intestine. It wraps around here, and then around here it becomes very convoluted. At this point, it splits in half. The brightest point, it splits in half. These lunar swirls are brightness features. They're albedo features. There's no topography associated with them. There are brightenings in the lunar surface. They usually take the form of lines or spots, usually with a bright lane with one or more adjacent dark lanes that parallel it. Many of them are sinuous like this. They move back and forth, almost like a stream. Their formation is a major puzzle. They are associated with magnetic anomalies. The moon has no net magnetic field, but these spots, these swirls, have strong magnetic fields, at least strong for the moon, associated with them. They appear to be related to basin impacts. These swirls are antipodal, that is, they're on the exact opposite side of the moon of major impacts, large basin impacts. And it seems to have something to do with either shock waves that have traveled through the moon from one side to the other, as they move away from the point of impact, they become attenuated and spread out. As they approach the other side, they'll come together again and become focused, that create large underground areas of disturbed material, fractured material, into which magma wells up and somehow becomes magnetized. The big puzzle about this, though, is that while these swirls clearly have something to do with basin impacts on the other side of the moon, the surfaces that they sit on are much, much younger than those impacts. That's a confusing thing to say. They appear to be expressions of something that had happened billions of years before these swirls actually formed and became visible. They look quite young because they're light colored. They're on surfaces that are younger than the impacts that caused them. So somehow, events that had happened 1 billion or 2 billion years later are showing up on the surface today as these swirls. One hypothesis, people have come up with fanciful ideas, like maybe these are the tails of comets that impacted on the moon. That doesn't work at all. One possibility, though, is that the magnetic field that was caused by these pockets of magnetized magma that seem to have collected on the opposite side of these impacts has somehow deflected the solar wind away from these lines and has prevented this surface here from aging. Remember, within a region, light generally means young, dark means old. This area here has been darkened by the solar wind. Perhaps the magnetic field has deflected those particles and prevented this material from aging. We really don't know, and there's a lot of research going on right now with these lunar swirls. As I mentioned, there are about 16 of them. This is another set of swirls right here. This is in the Mare Marginis. It's right along the lunar limb. It was caused by one of the largest recent impacts on the moon, the one that formed the Orientali Basin in the southwestern quadrant of the moon. It's located over here. It's difficult to see. This is one of the most difficult near-side swirls to image. What I've done here is take this part of the image and stretched it out to remove some of the foreshortening, and you can see these squiggly lines running through that mare. That represents these swirls. It can be fun in doing lunar imaging to try to image things that are hard to see, and this was my first attempt to do that. I wasn't even sure that I had gotten a good exposure of it until I stretched it out and could see exactly the same swirl patterns that were showing up in satellite photos like the Lunar Reconnaissance Orbiter. This is another challenging location. This is a structure that was discovered in a photograph that was taken during Apollo 15. They were looking, one of the Apollo 15 cameras looking out the window noticed an odd D-shaped depression. The depression is quite small. It's only 2 kilometers by 3 kilometers. And I've been trying to image this for a while and finally was able to find it. It's located on what is believed to be a volcanic plateau right here. It's in the debris field that's just to the east of the Imbrium Basin and dates back about 3.8 billion years. This was a volcano that came up in the fractured material on the edge of that basin. This is a blow up here of the photograph, and you can see this little D-shaped feature right there. It's about 3 kilometers long, 2 kilometers high, and then this is a recent Lunar Reconnaissance Orbiter photo of it. This is another lunar mystery. It's a depressed area on top of a volcanic plateau, which a volcanologist would say is likely a caldera, a volcanic vent that collapsed after the lava, the magma chamber beneath it retreated. But what's odd about this structure, and is not entirely explained, is that not only has this whole area been depressed as it fell into the magma chamber, but it appears that the soil is actually draining away into a porous layer beneath it. This is unique in the solar system. We haven't seen another structure like this. So recently I saw in another part of the moon, in another caldera, I got a hint of another structure that shows some drainage, but that's not widely recognized yet. So INA is a geological peculiarity. It's extremely difficult to image because it's small. And it's very gratifying using this video technique to be able to come up with a picture. This is a picture of it that I took earlier this week. This is that Lunar Reconnaissance Orbiter photo to scale now. This is that big volcanic plateau, and the light is coming from the right-hand side. So this is the bright side, the dark side. The plateau is it's about 1,000 meters above the area around it. Ina itself is this small feature right here, and it's only about 30 meters deep, and yet with the raking sun angle, I was able to get a nice shadow on the shadowed side and brightening on the illuminated side of it here. So I'm very, though that's a very fuzzy image, it's over-processed, it's too smooth. Nevertheless, I'm very proud I was able to catch that. A neat trick that you can use when you're shooting the moon is that because the moon is so close, we can image it in the daytime very well. This is a photograph from taken at the same time using a Canon digital camera. This was on a rather hazy morning, about 9 o'clock in the morning. This is an image taken using the video technique and my smallest telescope. I shot it through a red filter that will cut through a lot of that blue sky glare. While taking the image, I was very careful to adjust the contrast to get as much information about brightness as I could, and then processing it, you have to be very careful to not amplify the noise. When you take a very low contrast image like that and try to amplify the contrast, it's easy to overwhelm the picture with noise. But this is a nice technique that you can use for imaging the moon in the daytime. And this is an example of the Humoron basin over here on the southwestern quadrant of the moon that shows a tremendous amount of detail, even though it was taken in broad daylight. This was taken late in the morning. You can see the crater Descendi here, which is about 100 kilometers across, and the fractures on the floor of the crater that occurred when magma welled up and bowed up the basin of the crater. This is Doppelmayr, a crater that was flooded when the magmas welled up here in Humoron and spilled over the edge of that crater. There's a series of Mersenius rills, these cracks along here, and the Theopolis rills on that side, these cracks on that side, occurred when the magma welled up, depressed the floor, and then caused the edges of it to stretch out. And these parallel cracks ringing the basin occurred as the floor was being depressed from the weight of the dense lavas on top of it. But this is an example of what you can do even in the daytime with these video techniques. The video cameras we use often come in a monochrome version and a color version. Color is great if you're photographing planets because planetary details are often color details rather than just differences in albedo, differences in brightness. The problem with the moon, though, is it's an extremely gray object. There's very little real color in the moon, and when you look at color, when you use a color camera, most of the color you capture is false color. Oops. In this case, this is color on the edge limb of the moon that's caused by prismatic dispersion in the Earth's atmosphere. The Earth acts like a lens or a prism. The upper surface of the moon, in the sky, the upper part of the moon often has a bluish tinge. The lower part has a reddish tinge to it because the colors of the spectrum are being spread out by the Earth's atmosphere. Scattering is also important. If you take a photograph of the moon in the daytime, there's always a blue cast over the surface of it. This is scattered sunlight. If you take a photo of the moon at night as it approaches the horizon, the blue light from the moon is scattered, so the moon ends up looking very orange. The same thing happens to the sun in the daytime. And so scattering in the atmosphere will alter the colors in your photograph. This is a higher magnification image that shows a lot. I don't know if you can see that with this projector, but in the original, there's a lot of color noise in it. Pink pixels are directly adjacent to yellow pixels, which tells you that there's a lot of noise in your camera. And then often cameras have poor color balance. This bright feature here should be pure white, and yet it's coming in, the whole image looks brownish. So when we take a photograph of the moon in color, most of the color we see isn't real. So getting real colors in the moon is a challenge. I'm not going to read all of this to you, but we've got a technique for doing it. What we often do is to split out a black and white image and the color image, process them separately, and then put them back together again. The advantage of that is that from the black and white image, which we usually take from the sharpest of the color channels, in an RGB image, you have 3 color channels, red, green, and blue. Usually the red channel or green channel has a lot of contrast, a lot of sharpness in it. The blue channel will be blurred, it'll be washed out. So what we often do is take one of those color channels, separate that, and use it as a black and white channel. This gives us, we can use that to create, using the techniques we've talked about, like deconvolution and high dynamic range, toning, and sharpening. We can create a very sharp black and white image from that. We then take that color image, that RGB image, and we adjust it, the pixels, so that to remove that atmospheric dispersion so we don't see color fringes around bright craters anymore. We adjust the color balance so the highlights look bright white or gray, and then we blur it. The advantage of this, of blurring, is that it removes color noise. And so the colors of the pixels more accurately reflect the colors of that actual place on the moon. And then we saturate it to bring the colors out. When we take that sharp black and white image and superimpose it on top of that fuzzy color image, we end up with a very sharp color image. The eye uses differences in brightness from that black and white image to tell us where the boundaries are, and the color image to tell us what the colors are. And so though the brain apparently doesn't care whether you color within the boundaries as long as those boundaries are very sharp. And this is what when we split out a black and white image from a color one, we can come up with, we can create that sharpness. At the same time, we can improve the color by essentially blurring it, lowering its resolution. Here's an example of doing this. The colors on the moon reveal something about mineralogy. I've taken, this was a nearly full moon picture. In fact, this was a super moon from so-called super moon, term I hate, from last year, from 2013. I split it out a black and white image, increased the contrast, which showed the nice differences between the bright highlands and the dark seas, the dark lava seas. I then took the color image, blurred it, and saturated it. And this brought out the differences in mineralogy. On the moon, pink, this area in here, is associated with feldspar minerals. If you hold a chunk of feldspar, it often has a pink color to it. Blue represents titanium-rich lavas, and this brownish-greenish tone represents iron-rich lavas. So when we see colors on, when we bring out the colors on the moon, what we're actually revealing is the mineralogy of the surface. This is a higher resolution image of Tranquillitatis Basin and the Serenitatis Basin next to it. And you can see a very strong color contrast between the iron-rich lavas that are in the center of Serenitatis and these bluer lavas that are in Tranquillitatis. And this actually has this reveals something about the history here. That originally the lavas that erupted in this area were titanium rich and quite blue colored. Then in the center of Tranquillitatis, as those darker lavas, the bluer lavas, sank because of their high density, new lavas that were rich in iron spilled out on top of it. So in Serenitatis, you see a central core of these younger iron-rich lavas surrounded by a rim of much older titanium-rich lavas. Lunar geologists love color photos like this because they reveal a lot about not just the mineralogy but the history of the lunar surface. Now we can use these same video techniques when we photograph other solar system objects. This is a sunspot, a large sunspot group that I'm sure Freddie remembers from 2013. By using the same stack and then process technique, we can bring out very fine lunar details. These are tubules of plasma around a sunspot that look as though they're revealing some depth to that core of the sunspot. Yeah?
How long a time span was that over? Because those granulations come and go pretty fast.
These granulations out here are, of course, convection cells of material bubbling up from the solar interior. You can take an image an hour apart, and these convection cells will have all changed.
Yeah.
Yeah. The tubules around the sunspots don't change that rapidly. They're following magnetic field lines, and they're a little bit more stable than that. Although you can see, I mean, from hour to hour, you can see changes. These tubules seem to have a longer life than the convection cells.
So the
These
sharp
granules do not.
granulations mean this was a rather short overall time span.
Yeah, I mean, the image itself, I took the image over, this was a 2-minute capture.
Okay.
So it was probably about 2,000 frames. And in that time, you don't see a lot of changes. This is an image of Mars that I used that same. Now the color here is false color. This was done using a black and white camera and the same sort of beta solar film that Freddie talked about. And then I colorized the image after I did it. It's looking at a purely black and white grayscale image of the sun isn't very interesting. And just giving it a little bit of warmth makes it feel a lot more real. This is an image of Mars from the last opposition of Mars, pulling out a lot of detail. This is the best image of Mars I've taken. It even shows clouds in the Hellas Basin down here, which is very nice. And this is an okay image of Jupiter. I think I have a couple better ones, but it shows the great red spot very nicely, and then very turbulent material, very turbulent clouds coming off of one of the equatorial bands, traveling past the great red spot. So that's got some nice detail in it. But these are processed using exactly the same kind of techniques that we use for looking at the moon. Now, Freddie mentioned using DSLR and point-and-shoot cameras. These take a single image. And this is an example of a point-and-shoot image I took using my 18-inch Dobsonian. This is a large, unguided telescope. I simply took a Sony pocket camera, an 8-megapixel pocket camera, stuck it up to the eyepiece and took a snapshot. And it's not a terrible picture. It's not a terrible picture. Oddly, I find that my little Sony point-and-shoot takes better pictures than my Canon DSLR that's got an 8-megapixel sensor. So the camera and the point-and-shoot cost $200. The DSLR cost a couple thousand. So the price of the camera doesn't tell you anything about the quality of images it's going to take. But the image is a little bit fuzzy. There's a lot of false color in it, and we've lost a lot of definition close to the terminator here. There's actually a lot. This area is under faint illumination, and there is some detail. Now we can use a technique similar to the way we process color photos to bring out information here. The first step, and you can do this in Photoshop or other photo processing programs, is to split out the different color channels. There's not enough real color information in that point-and-shoot image to try to process in color. So it makes sense to process this in black and white. When you look at the separate color channels here, this is a red image, this is the green channel, this is the blue channel. The blue channel is much darker in this case. It's also much noisier. The red and the green channels have more definition in them, and at least when I enlarged it, the green channel had slightly better contrast than the red channel, which seemed to be a little washed out in this area. So I took that green channel and then processed it in mono, using the same kind of techniques that we've been doing. I made a black and white image of the green channel. I used very gentle deconvolution, a little bit of high dynamic range toning and sharpening. And that gave me this image over here on the right. And you can see that that we've got more information showing out here close to the terminator. There's more contrast, like these wrinkle ridges. This is the edge of the Sea of Rains, of the Mare Imbrium, that big impact basin. The rim of that basin here, that's with this hummocky ejecta in it, is better defined than it was in the original color image. The Alpine Valley right here is a little bit sharper. The shadows of the peaks along the rim of Plato come through very nicely in that image there. This is an enlargement of the area around the Alpine Valley. And while the difference is subtle, The black and white image here does have more information in it and is showing more detail. If the projector was a little bit sharper, you can actually see in this image a very faint rill, a very faint valley running in the center of the Altai Valley, just about a kilometer across, which is completely invisible in the color image. So even in this relatively mediocre color image, from a point-and-shoot camera, with a little bit of processing, we can bring out much more information and make a much more pleasing picture. Similarly, this is a moon just after first quarter. In the point-and-shoot image here, the terminator looks a bit ragged in places because of where it crosses these dark seas, the dark mare. This area here looks washed out because it was quite bright in the image. By applying these kinds of techniques, first converting this to a mono image using, I think once again, this is the green channel, and then processing that like our video images to bring up the contrast, to enhance the sharpness, we come up with a much more pleasing image that has the same amount of information in it, but now that information is more visible and becomes apparent in the picture. This is the equipment that I use. Freddie and I use different software. He likes to use iCap for his captures. I use a program called Fire Capture, which works well with the camera. I like to use the ASI 120 mono version. To deblur, I use a special purpose program called Astra Image. Sometimes I'll use the wavelength processing in specs. And then I do the rest in Photoshop. If you're doing astronomical image processing, I do have a recommendation. Photoshop is great. You can use the full version or the reduced version of it. It's much more affordable. But I would strongly recommend that you get the full set of Topaz Labs filters. Topaz Labs, these are filters designed for professional photographers. They include high dynamic range toning, sharpening, denoising, and also some deblurring algorithms. These are very easy to use filters that are much more powerful than the native filters that are in Photoshop and are great for for processing lunar and planetary photos. And I promise that over the next 2 weeks, I'll be putting my lunar images on my website. So I should have an archive of those. So that's the talk.